Welcome to the Late Lab. It's really lovely to have you here. Before we settle in, where in the world are you watching from tonight? Are you tucked away in a quiet bedroom, listening beneath a blanket, drifting on a late train, or sitting somewhere peaceful with the lights turned low and the day finally beginning to loosen its grip? Wherever this finds you, hopefully you are warm, comfortable, and ready to let your thoughts wander somewhere strange and very small. If you enjoy these calm journeys through science and would like more of them, a like and subscribe helps this little sleepy channel keep floating through the algorithmic fog. And to everyone already subscribed, thank you, truly. Your support makes all of this possible, and it is appreciated more than you know. Now, tonight's subject is one of those topics that comes with a gentle warning. Quantum physics is supposed to be relaxing, at least in this corner of the internet, but it also has a habit of making reality look suspiciously less solid than it did a few minutes ago. With any luck, that will be interesting enough to keep you listening, but not so interesting that you end up staring at the ceiling at 2 a.m. wondering whether the ceiling is technically a probability cloud. That would be inconvenient, though admittedly quite on theme. So let's begin, shall we? What is quantum physics, and why does the universe seem to behave so strangely when science looks at it closely? A barrier is one of the simplest ideas in ordinary life. A wall stops you walking forward. A locked door waits patiently for a key. A hill will not let a rolling ball reach the other side unless the ball has enough energy to climb up and over it. The everyday world is full of these quiet refusals. Things either have enough energy to cross a boundary, or they do not. A stone thrown gently at a brick wall does not appear calmly on the other side, looking innocent and pretending nothing unusual has happened. It bounces back, falls down, and resumes its career as a stone. This is the world classical physics describes so beautifully. It is the world of familiar objects, definite paths, clear causes, and barriers that mean what they appear to mean. If a ball is rolling toward a hill and does not have enough speed to reach the top, it will slow, stop, and roll back down. No hidden option exists where the ball simply appears beyond the hill because it felt like taking a shortcut. Classical physics is not fond of that sort of behaviour. It likes its objects accountable. It wants them to explain where they have been. But quantum physics begins in a much smaller world, and in that world, barriers become stranger. At the scale of atoms and particles, nature does not always behave like a smaller version of everyday life. An electron is not just a tiny bead moving along a neat invisible track. A proton is not simply a microscopic billiard ball. A particle in quantum mechanics is described by a wave function, which carries information about the possible places and states in which that particle may be found. This does not mean the particle is a blurry little cloud in the ordinary sense, as if it has been smudged with a tiny cosmic paintbrush. It means that before measurement, quantum physics gives a spread of possibilities rather than one perfectly settled classical story. This is where the first deep strangeness enters. In classical physics, a barrier is often absolute. If a particle does not have enough energy to cross it, then it stays on its own side. The answer is no. The door is shut, the hill is too high, the account is settled. But in quantum mechanics, the wave function associated with a particle can extend into a region that classical physics would call forbidden. Inside that region, the wave function usually fades very quickly. The thicker or higher the barrier is, the more sharply it fades. Yet in some cases it does not fade all the way to nothing before reaching the other side, and if some part of that wave function remains beyond the barrier, there is a real probability that the particle will be detected there. That process is called quantum tunneling. The name is useful but slightly misleading. The particle is not digging a physical tunnel through matter like a very determined subatomic mole. It is not smashing through the barrier, sneaking around the side or finding a tiny secret doorway left open by a careless universe. Quantum tunneling is not a mechanical trick, hiding inside the wall. It is a consequence of the wave-like mathematical structure of quantum theory. A particle has a probability of being found beyond a barrier even when, according to classical physics, it does not have enough energy to cross that barrier in the ordinary way. That sounds impossible only because ordinary experience has trained the mind to expect solid things and definite paths. Human intuition was built in a world of tables, floors, cups of tea, weather, footsteps, doors, hills, and occasionally the rude surprise of walking into furniture in the dark. In that world, objects are large, warm, and constantly interacting with their surroundings. Their quantum behavior is still present underneath everything, but it is hidden beneath a great crowd of interactions. The strangeness is there, but it does not announce itself every time a chair decides to remain politely chair-shaped. At tiny scales, however, the underlying rules become hard to ignore. Quantum tunneling is one of the clearest examples of the difference between what seems possible in the familiar world and what is allowed in the quantum world. It does not say that anything can happen in a loose or magical sense. It does not turn physics into a collection of random miracles. Instead, it replaces the hard certainty of classical barriers with probabilities that can be calculated, tested, and used. A particle may tunnel or it may not. The chance may be high enough to matter, or so unbelievably tiny that for all practical purposes it might as well be zero. But the important point is that the chance is not always exactly zero, that small opening changes an enormous amount. Quantum tunneling helps explain certain forms of radioactive decay, especially alpha decay, where a particle trapped inside an atomic nucleus can escape through a barrier created by the forces inside the atom. It helps explain why the sun can shine steadily, because protons in the sun's core can sometimes tunnel close enough together for nuclear fusion to occur, even though their positive electric charges repel each other. It appears in technologies built by human hands, including tunnel diodes, flash memory, Josephson junctions, and the scanning tunneling microscope, an instrument so precise that it can help scientists study surfaces atom by atom. So this strange effect is not a decorative curiosity placed at the edge of physics. It is part of the working machinery of the universe. Without tunneling, the story of stars would be different. The story of atoms would be different. The story of modern electronics would be different. A quiet quantum possibility, invisible to ordinary senses, helps shape the warmth of sunlight and the behavior of devices sitting casually in pockets and on desks, looking far too ordinary for the amount of quantum mischief involved. What makes tunneling especially useful as an entrance into quantum physics is that it shows the deeper pattern very clearly. The quantum world is not strange because it is vague. It is strange because it is precise in a way that does not match the habits of everyday imagination. Classical physics often speaks in definite paths and fixed outcomes. Quantum mechanics speaks in wave functions, probabilities, measurements, and allowed possibilities. It does not always tell the same kind of story the human mind expects, but it tells a story that experiments keep confirming with remarkable accuracy. And tunneling is only the first doorway. The same quantum logic that allows a particle to appear beyond a barrier also leads toward other unsettling ideas. Atoms are stable because electrons do not orbit nuclei like little planets in a simple solar system, but occupy quantum states described by probabilities. Light behaves as both wave-like and particle-like, depending on how it is studied. Measurement seems to play a special role in turning possible outcomes into observed ones. Entangled particles can share a joint quantum state even when separated by large distances, though not in a way that allows faster-than-light messages. Empty space itself in quantum field theory is not a blank nothing, but a structured state of underlying fields. Each of these ideas has its own careful scientific meaning. None of them require mysticism, wishful thinking, or pretending that reality is whatever anyone wants it to be. Quantum physics is much stranger than that, and much stricter. It allows possibilities ordinary intuition would never have guessed, then gives them mathematical rules so exact that they can be used to build lasers, atomic clocks, medical scanners, computer chips, and instruments that probe the smallest known structures of matter. A barrier, then, is not always the simple refusal it appears to be. In everyday life, walls remain walls, and it is wise not to test otherwise with enthusiasm. But beneath the everyday world, in the quiet language of particles and wave functions, a barrier can become something more subtle. Not an open road, not a broken rule, not an invitation for large objects to wander through solid matter without consequences. A barrier becomes a question, and in the strange world of quantum physics, nature sometimes answers that question with a very small, very real maybe. The idea of a particle is deceptively comforting. It suggests something tiny, solid, and self-contained, like a grain of dust made smaller and smaller until it becomes part of the hidden architecture of matter. It is easy to imagine an electron as a little bead, a proton as a smaller marble, an atom as a miniature solar system, and light as a shower of sparkling fragments racing through space. These pictures are useful in the beginning because they give the mind something to hold. But they are also misleading if they are taken too literally. The early 20th century forced physics to let go of that comfortable picture. Scientists had become extremely good at describing the large-scale world. Isaac Newton's laws explained motion with astonishing power. James Clerk Maxwell's equations described electricity, magnetism, and light as parts of one elegant electromagnetic framework. Thermodynamics explained heat, energy, and pressure. To many physicists, it seemed as though the deep rules of nature were nearly complete, with perhaps a few awkward corners left to tidy. Physics had become a very grand house with only a little dust behind the furniture. Unfortunately, the dust turned out to contain the quantum world. One of the first cracks appeared in the study of black body radiation. A black body is an idealized object that absorbs and emits radiation in a way that depends on its temperature. The problem sounds fairly gentle, almost domestic, like studying why warm objects glow. But when physicists tried to describe the exact pattern of light emitted by a hot object, classical physics gave answers that failed badly at short wavelengths. The predictions did not simply miss by a little. They pointed toward an impossible result, where the emitted energy would become absurdly large. This failure became known later as the ultraviolet catastrophe, which is a wonderfully dramatic name for a mathematical disaster involving hot objects. Science does occasionally have flair. In 1900, Max Planck found a way out. He proposed that energy was not exchanged in any smooth amount, but in tiny discrete portions. These portions became known as quanta. Planck did not begin by trying to overthrow reality. He was trying to solve a technical problem in radiation physics, but the solution carried a revolutionary implication. At the smaller scales, energy might not flow continuously, like water from a tap. It might arrive in packets, like tiny measured parcels. This was the quantum hypothesis, and it quietly changed everything. A few years later, Albert Einstein pushed the idea further while studying the photoelectric effect. In this effect, light shining on certain materials can knock electrons out of them. Classical wave theory suggested that brighter light should eventually give electrons enough energy, because a stronger wave carries more energy. But experiments showed something stranger. The colour or frequency of the light mattered in a very precise way. Below a certain frequency, no electrons were emitted no matter how intense the light became. Above that frequency, electrons could be released. Einstein explained this in 1905 by treating light as if it came in discrete packets of energy, later called photons. Each photon carried an amount of energy related to the frequency of the light. If one photon had enough energy, it could free an electron. If it did not, piling on more low-energy photons would not solve the problem in the same simple way. Light, which Maxwell had so beautifully described as a wave, now also seemed to behave like a stream of particles. This was not a small adjustment. It was a quiet betrayal of common sense. Light had wave-like properties. It could interfere with itself, spread out and create patterns of brightness and darkness. Yet it also behaved in particle-like ways when interacting with matter. The universe seemed unwilling to choose one familiar category and remain there politely. A photon was not simply a little marble of light, but neither was it just an ordinary wave like a ripple on a pond. It belonged to a deeper category, one that ordinary language struggles to describe, because ordinary language was not raised among photons. Then the strangeness widened again. If light, once thought to be purely wave-like, could behave like particles, perhaps matter, once thought to be purely particle-like, could behave like waves. In 1924, Louis de Broglie proposed exactly that. He suggested that particles such as electrons have wave-like properties. This idea, known as matter waves, was not just a poetic comparison. It made testable predictions. Electrons could produce diffraction and interference patterns, behaviors that had been associated with waves. Experiments soon supported this. The Davison-Germer experiment in the late 1920s showed electron diffraction from a crystal surface, giving strong evidence that electrons really do have wave-like behavior. The electron, one of the basic ingredients of matter, was not behaving like a simple tiny ball. It could act like something spread out enough to interfere, diffract, and reveal a wavelength. This is the heart of wave-particle duality. Quantum objects such as photons and electrons are not sometimes normal particles, and sometimes normal waves in the everyday sense. Rather, they are quantum objects, and depending on how they are prepared and measured, they show features that remind us of both. The words wave and particle are borrowed from ordinary experience, but quantum objects are not obliged to fit neatly inside either word. They are not tiny marbles, they are not tiny water ripples, they are something more subtle. This matters because tunneling only begins to make sense once the marble picture is loosened. A marble approaches a hill with a definite position, a definite path, and a definite amount of energy. If the hill is too high, the marble stops and rolls back. That picture works beautifully for large objects. But a quantum particle is described by a wave function, a mathematical description connected to the probabilities of where it may be found and what may be measured. When that quantum object meets a barrier, its wave-like description does not simply stop dead at the edge like a tennis ball hitting a wall. The wave function can extend slightly into the barrier. Usually it fades rapidly. If the barrier is too wide or too high, the chance of finding the particle beyond it becomes vanishingly small. But if the conditions are right, part of the wave function can reach the far side, leaving a real probability that the particle will be detected there. That is why the early quantum revolution matters so much. Planck's quanta showed that energy itself could have a graininess at small scales. Einstein's photons showed that light could behave as if it arrived in packets. De Broglie's matter waves showed that matter could not be understood as simple solid specks. Each step weakened the old assumption that the tiny world must simply be a smaller copy of the familiar one. The atom is not a little clockwork model. An electron is not a planet. A photon is not a glowing pebble. A quantum object is described through probabilities, interactions, energy levels, wave-like behavior, and measurement outcomes. The strangeness is not decorative. It is the working grammar of matter and light. And once particles are no longer tiny marbles, the barrier no longer has to mean what it means in everyday life. It can still be a real barrier. It can still make crossing unlikely. But quantum physics leaves room for a faint continuation, a fading possibility, a small mathematical tail reaching into the forbidden region. In that quiet extension, tunneling becomes possible. The universe does not need a hidden trapdoor. It only needs particles that were never marbles in the first place. A particle that is not a tiny marble needs a different kind of description. It cannot be followed in quite the same way as a pebble thrown through the air, or a planet moving around the sun, or a sleepy cat crossing a room with the grave importance of a small aristocrat. In the familiar world, objects seem to have definite positions, definite paths, and definite properties whether anyone is checking or not. They're here, then there, then somewhere else, as if reality is quietly keeping a neat little ledger. Quantum physics does not give that kind of picture so easily. Instead, one of its central ideas is the wave function. The wave function is the mathematical description used in quantum mechanics to represent the possible states of a quantum system. It may describe where an electron could be found, what energy state an atom may occupy, how a particle's momentum is distributed, or how several quantum properties fit together before a measurement is made. It is not a tiny physical mist floating around the particle in the ordinary sense. It is not a water wave, a sound wave, or a ripple travelling across a pond. It is something more abstract and more powerful, a structured description of possibility. That word, possibility, matters. Classical physics often describes what is. Quantum mechanics often describes what may be found when nature is asked a particular question in a particular way. The wave function contains the information needed to calculate the probabilities of different measurement outcomes. It does not simply say, "Here is the particle, sitting politely at this exact location, waiting to be noticed." It gives a spread of possible results, each with its own probability, and that spread evolves according to strict rules. One of the most important people in giving quantum physics this wave-like form was Erwin Schrödinger. In the mid-1920s, Schrödinger developed wave mechanics, a way of describing quantum systems through wave functions that change over time. His famous Schrödinger equation became one of the foundation stones of quantum theory. It tells physicists how the wave function of a system evolves, in much the same broad sense that Newton's laws tell physicists how a classical object moves. But what evolves in Schrödinger's theory is not a tiny billiard ball travelling along one perfect path. It is the wave function itself, the mathematical shape of possible outcomes. This was a profound shift. It meant that a quantum object could not always be pictured as something simply sitting in one place before it was measured. An electron in an atom, for example, is not a little planet circling the nucleus on a narrow track. It is described by an orbital, a quantum state connected to a probability distribution around the nucleus. The electron is not smeared out because the instruments are poor, or because science has misplaced it under the sofa. The quantum description itself is built from probabilities. At first, even this idea needed interpretation. If the wave function was so central, what did it physically mean? Was it a real wave? Was it only a calculation tool? Was it something deeper still? These questions have not entirely vanished, and physicists still discuss the interpretation of the wave function today. But one crucial step came from Max Born. Born proposed that the wave function should be understood through probability. More precisely, the mathematical size of the wave function at a location is connected to the probability of finding the particle there when a measurement is made. This idea became known as the Born rule. It turned probability from a sign of ignorance into a central feature of quantum mechanics. In classical physics, probability often enters because the situation is too complicated to track perfectly. A coin toss is not truly mysterious in the same quantum sense. In principle, if every detail of the coin, air, hand, surface and motion were known exactly, the result could be predicted. The probability comes from practical ignorance. Quantum probability is different. It appears to be woven into the structure of the theory itself. That is one reason quantum physics can feel so strange. It does not merely say that humans do not know where the particle is, it says that the most successful description of the particle before measurement may be a spread of possible outcomes. The wave function can be concentrated in one region, spread across several regions, or arranged so that different possibilities interfere with one another. These features are not optional decorations. They are why quantum theory explains atomic spectra, chemical bonding, lasers, semiconductors, and the behavior of matter with such extraordinary success. The wave function can also extend into places that classical physics would forbid. That is where the connection to tunneling becomes direct. Imagine again a particle approaching a barrier. In classical physics, if it lacks enough energy to cross, it cannot appear on the other side. The story ends at the barrier. But in quantum mechanics, the wave function does not usually stop with a hard theatrical thud. At the boundary of the barrier, the wave function can continue into the forbidden region, though it usually becomes smaller as it does. The probability associated with finding the particle inside the barrier drops rapidly. Yet if the barrier is thin enough, or if the conditions are suitable, the wave function may still have a small but non-zero presence beyond the far side. Non-zero is the quiet phrase that changes the whole story. A non-zero probability does not mean tunneling is guaranteed. It does not mean the particle has secretly broken the rules. It means that the quantum rules never gave the same absolute answer that classical physics would have given. The wave function assigns a small chance to an outcome that would be impossible in the older picture. When many particles are involved, or when a process repeats over and over, even small probabilities can become deeply important. This is how tunneling becomes relevant in radioactive decay, nuclear fusion in stars, and delicate electronic devices. The shape of the wave function therefore shapes what can happen. If the wave function is tightly confined, the possible measurement outcomes are narrow in one way, but may be broad in another. If it is spread out, the particle may have a wider range of possible locations. If wave functions overlap, quantum systems can interfere, reinforce some outcomes, and suppress others. These are not visual metaphors in the ordinary sense, but they help point toward the underlying mathematics. Quantum theory is not saying that reality is fuzzy because science is confused. It is saying that the basic description of tiny systems is not built from hard little objects with hidden classical roots. And this is why the wave function is so important to the strange world of quantum physics. It is the bridge between mathematical law and physical possibility. It shows how a particle can be described without imagining it as a miniature marble. It explains how probability can be precise rather than vague. It reveals why a barrier may not be an absolute ending, but a region where possibility fades. In everyday life, possibility often means a thought, a guess, or a hope. In quantum physics, possibility has structure. It can spread, shrink, overlap, interfere, and leave a faint trace beyond a boundary that common sense would have declared final. The wave function is the structure written in mathematical form, quietly guiding the strange behavior of matter and light. A particle does not need to know where it is going. It does not need a secret passage through the wall. It only needs a wave function that has not quite vanished on the far side. And sometimes, in the small and patient language of quantum mechanics, that is enough. Quantum tunneling is one of those ideas that sounds as if it should belong in science fiction, but it sits firmly inside real physics. It is not a decorative oddity. It is not a poetic way of saying that particles are mysterious. It is a measurable quantum process in which a particle has a chance of being detected beyond a barrier, even when classical physics says it does not have enough energy to cross that barrier in the ordinary way. In the familiar world, barriers behave with a certain blunt honesty. A ball rolling toward a hill needs enough energy to reach the top. If it has enough, it passes over. If it does not, it rolls back down, perhaps with the quiet embarrassment of an object that overestimated itself. A person standing before a wall cannot simply appear on the other side by being described mathematically in a more adventurous mood. Ordinary objects are stopped by ordinary barriers, and that expectation works so well in daily life that it feels almost impossible to imagine nature doing anything else. But quantum physics does not begin with ordinary objects. It begins with things like electrons, protons, atoms, and photons, where the most useful description is not a tiny solid bead following one exact path, but a wave function connected to possible measurement outcomes. This wave function can extend across space, it can spread, it can shrink, it can change, shape with time. Most importantly for tunneling, it does not always stop sharply at the edge of a barrier. A barrier, in this context, does not have to mean a wall made of bricks. It means a region where the particle would need more energy than it appears to have in order to pass through in the classical sense. That barrier might be created by electric repulsion, as in the case of charged particles pushing away from each other. It might appear inside a material, where electrons face an energy boundary between one region and another. It might arise in the nucleus of an atom, where competing forces create a trap that is not completely final. The details differ, but the central idea remains the same. Classical physics says the particle cannot cross. Quantum mechanics says the answer is not always so simple. When a quantum particle meets a barrier, its wave function can enter the classically forbidden region. Inside that region, the wave function usually decreases very quickly. It fades, often dramatically, like a sound becoming softer as it passes through a thick wall, though that comparison is only a guide and not a literal picture. The wave function is not sound, water, fog, or a tiny physical rope being pulled through matter. It is the mathematical structure used to calculate the probabilities of finding the particle in different places. If the barrier is thick enough, the wave function may become so small before reaching the far side that the chance of finding the particle beyond it is effectively zero. But if the barrier is thin enough, or low enough, or the particle is light enough, then a faint part of the wave function can remain on the other side. That faint part corresponds to a small but real probability. When a measurement is made, the particle may be found beyond the barrier. This is quantum tunneling. The particle has not smashed through the wall like a microscopic battering ram. It has not discovered a secret tunnel that was hiding there all along. The word tunneling is helpful because it gives the imagination something to hold, but it can also make the process sound too mechanical. Nothing is digging. Nothing is chewing through a barrier with tiny, determined teeth. The particle is behaving according to the rules of quantum mechanics, where probability can extend into regions that classical physics would declare forbidden. Several things shape how likely tunneling is. The height of the barrier matters. A higher barrier usually makes tunneling less likely, because the wave function fades more strongly inside it. The width of the barrier matters as well. A thin barrier may allow enough of the wave function to remain on the far side. A wide barrier gives the wave function more distance over which to shrink, leaving almost no probability beyond it. The particle's energy is also important. If the particle's energy is closer to the top of the barrier, tunneling becomes more likely than if it is far below. And the particle's mass matters too. Lighter particles, such as electrons, are much more likely to show tunneling behavior than heavier objects. This is one reason quantum tunneling belongs mostly to the tiny world. Electrons can tunnel through very thin barriers in electronic devices. Protons and alpha particles can tunnel in nuclear processes. Atoms can show tunneling under the right laboratory conditions. But a human body, a chair, a book, or a cup of tea tunneling through a wall is not a realistic possibility in any practical sense. The probability is not merely small in the everyday meaning of small, it is so fantastically tiny that the word tiny begins to feel overworked and underpaid. A human body contains an enormous number of particles, all interacting with one another and with the surrounding environment. For the whole body to tunnel through a wall, all those particles would need to behave in a coordinated quantum way that preserves the object as a person, rather than turning the situation into an extremely confusing physics problem. The probability of that happening is so close to zero that it can safely be treated as impossible for ordinary life. Walls may continue feeling confident in their professional role. This distinction is important. Quantum physics does not say that anything can happen just because the universe is strange. It says that certain outcomes, forbidden by classical reasoning, can have calculable probabilities under quantum rules. Sometimes those probabilities are large, enough to matter. Sometimes they are so small that nature, for all practical purposes, never takes that route. Quantum tunneling is not a permission slip for fantasy. It is a precise effect with strict conditions. That precision is what makes tunneling so powerful. In radioactive decay, tunneling helps explain how particles can escape from an atomic nucleus. In the Sun, tunneling helps protons get close enough for nuclear fusion to occur, allowing sunlight to exist in the gentle, steady way life on Earth depends on. In technology, tunneling appears in devices such as tunnel diodes, flash memory, and scanning tunneling microscopes, where the effect is not merely observed but deliberately used. A phenomenon that sounds impossible becomes part of the machinery of both stars and circuits. Tunneling is therefore one of the clearest windows into the strange world of quantum physics. It shows how reality at small scales is not built from definite little objects obeying only the familiar habits of everyday experience. It is built from wave functions, probabilities, energy barriers, and measurement outcomes. The ordinary world still emerges from these rules, solid and reliable enough for floors, walls and furniture to remain reassuringly unadventurous. But underneath that familiar calm, nature allows possibilities that classical physics would never have accepted. A barrier can still be a barrier. It can still make crossing unlikely. It can still stand there, doing its quiet job. But in the quantum world, it is not always the end of the story. Sometimes, beyond the barrier, there remains the faintest mathematical trace, and sometimes that faint trace is enough for reality to choose the other side. One of the clearest places to see quantum tunneling at work is inside the atomic nucleus, in the quiet, unstable heart of certain radioactive atoms. Here, the idea of a particle escaping through a barrier is not just a thought experiment or a strange laboratory trick. It becomes part of the natural behavior of matter itself. Radioactive decay shows that the quantum world does not merely behave strangely when physicists arrange delicate experiments. Sometimes the strangeness is already built into the elements around us, patiently unfolding atom by atom. A particularly important example is alpha decay. In alpha decay, an unstable atomic nucleus releases an alpha particle, which is made of 2 protons and 2 neutrons. This is the same structure as the nucleus of a helium atom, though without the surrounding electrons. Many heavy elements such as uranium, radium and polonium can decay in this way. The nucleus begins in an unstable state, and at some unpredictable moment, an alpha particle appears outside it, carrying energy away. At first, this seems like a puzzle. Inside the nucleus, the alpha particle is held by the strong nuclear force. This force is one of the fundamental forces of nature, and at the tiny distances inside atomic nuclei, it is extremely powerful. It binds protons and neutrons together, overcoming the electric repulsion between positively charged protons. Without the strong nuclear force, atomic nuclei as we know them would not hold together. Matter would have had a rather disappointing start, but the strong nuclear force has a very short range. It is powerful when particles are extremely close, but it fades quickly over nuclear distances. Outside the nucleus, another influence becomes important: electric repulsion. An alpha particle has a positive electric charge, and the rest of the nucleus is also positively charged. Like charges repel, so the alpha particle faces an energy barrier as it tries to leave. It is held in by the nuclear attraction at very short distances, but to escape completely, it must get through a barrier created largely by electromagnetic repulsion. Classically, this can seem impossible. The alpha particle often does not appear to have enough energy to climb over that barrier in the ordinary way. It is as if it is trapped in a valley surrounded by a hill too high to cross. In classical physics, the answer should be simple. If it cannot climb over the hill, it stays where it is. The nucleus should remain unchanged. The alpha particle should remain trapped, and that should be the end of the story. But radioactive atoms do decay. The explanation came from quantum tunneling. In 1928, George Gamow developed a quantum explanation of alpha decay, and around the same time, Ronald Gurney and Edward Condon also showed how tunneling could account for the escape of alpha particles from nuclei. Their work connected the newly developing quantum theory to a real and puzzling nuclear process. The alpha particle could be described by a wave function inside the nucleus, and that wave function did not simply stop at the nuclear barrier. It could extend into the forbidden region. Most of it faded rapidly, but a small part could reach beyond the barrier, leaving a real probability that the alpha particle would be found outside. This did not mean the alpha particle forced its way out through a physical tunnel. It did not crack open the nucleus like a tiny escape artist with a very small crowbar. The word tunneling is a helpful image, but the process is subtler than that. The alpha particle is governed by a wave function, and the shape of that wave function gives a probability of escape. If the barrier is high and wide, the probability is very small. If the barrier is lower or narrower, the probability becomes larger. Over time, those probabilities determine how often decay occurs. This is where radioactive decay becomes deeply quantum. It is probabilistic. For one unstable atom, physics cannot say exactly when it will decay. It may happen soon, or it may happen much later. There is no hidden clock inside the atom, ticking down in a simple mechanical way. The best description gives a probability of decay over time. This is not because scientists have failed to notice some obvious little timer. It is because quantum theory itself describes the process through probability. Yet the randomness is not chaotic. This is one of the quietly beautiful features of radioactive decay. A single atom behaves unpredictably, but a large collection of atoms follows a very reliable statistical pattern. If there are enough unstable nuclei, their collective behavior becomes smooth and measurable. This is how half-life becomes meaningful. A half-life is the time it takes for half of a sample of radioactive atoms to decay on average. It does not mean that every atom waits politely until the half-life has passed, and then half of them raise their hands. Individual atoms do not form a schedule. Instead, each atom has a certain probability of decaying in a given period of time. When vast numbers of atoms are present, those probabilities produce a steady pattern. Half the original atoms remain after one half-life, a quarter remain after 2, an eighth remain after 3. The exact atoms that decay are not individually predictable. but the overall pattern is astonishingly dependable. Quantum tunneling helps explain why different radioactive materials have such different half-lives. Some decay very quickly because the probability of tunneling is relatively high. Others last for thousands, millions, or even billions of years because the tunneling probability is extremely low. Uranium-238, for example, has a half-life of about 4.5 billion years. That enormous span is tied to how rarely its alpha particles tunnel out of the nucleus. Polonium isotopes can decay much more quickly because their nuclear conditions give much higher probability of escape. The difference is not simply that one atom is impatient and another has excellent long-term planning skills. It comes from the structure of the nucleus, the energy of the alpha particle, and the height and width of the barrier it must tunnel through. A small change in these conditions can produce a huge change in decay rate. This is one reason the quantum explanation of alpha decay was so powerful. It helped make sense of the wide range of observed radioactive half-lives using the same underlying principle. Alpha decay therefore deepens the story of tunneling. It shows that quantum probability is not just an abstract idea floating around in equations. It affects real atoms. It changes elements. It releases energy. It contributes to natural radioactivity in rocks, planetary interiors, and laboratory samples. The heat produced by radioactive decay inside Earth helps drive geological activity over immense timescales, quietly linking quantum physics to the warmth of the planet beneath our feet. It also reveals something important about randomness. In ordinary speech, random often means messy, meaningless, or impossible to understand. But quantum randomness can be highly structured. The decay of one atom cannot be predicted exactly, yet the decay of a large sample can be described with remarkable precision. There is uncertainty at the individual level and order at the collective level. Nature seems to roll dice, but over large numbers it keeps excellent accounts. Radioactive decay is unsettling for exactly that reason. It joins unpredictability with reliability. It shows an alpha particle escaping from a nucleus, not because it climbed over the barrier, and not because it broke the rules, but because the quantum rules allowed a small probability of being found outside. The event is sudden when it happens, but the possibility has been present all along, faintly written into the wave function. Inside the nucleus, then, tunneling is not a strange exception. It is a working part of matter. A particle held by one force and resisted by another can still escape, not by force, not by luck in the ordinary sense, but through the precise mathematics of quantum probability. The atom does not know when it will decay. No observer can point to one nucleus and name the exact moment in advance. But across countless atoms, the pattern emerges with calm regularity, as if randomness itself has learned to breathe in rhythm. Sunlight feels like the most ordinary thing in the world. It slips across curtains in the morning, warms stone, feeds forests, glitters on water, and gives the sky its familiar blue. It seems calm, steady, and almost effortless, as if the sun is simply doing what suns do, shining away with enormous confidence. But deep inside that familiar light is a quantum process so strange that, without it, the sun would not shine in quite the way it does. At the centre of the sun, conditions are extreme by any earthly standard. The core reaches temperatures of roughly 15 million degrees Celsius, and the pressure is immense because the weight of the outer layers presses inward under gravity. Matter, there is not arranged as ordinary gas with atoms calmly keeping their electrons. It is plasma, a hot sea of charged particles where atomic nuclei and electrons move freely. The sun's core is dense, hot, and restless, with particles constantly colliding in a brilliant hidden storm. This sounds as if fusion should be easy. After all, 15 million degrees is not exactly a mildly warm afternoon. It is a temperature so high that ordinary language begins to run out of sensible comparisons and quietly backs out of the room. Yet for nuclear fusion, the problem is not simply heat. The problem is that the particles that need to fuse are often positively charged protons, and positively charged particles repel each other through the electromagnetic force. This repulsion creates a barrier. Two protons approaching one another behave a little like two magnets brought together the wrong way round. The closer they come, the more strongly they push apart. For fusion to happen, the protons must get extremely close enough for the strong nuclear force to take over. The strong nuclear force is powerful enough to bind particles together inside nuclei, but it works only across very tiny distances. It is like a very strong hand with an extremely short reach. Until the protons get close enough, electric repulsion keeps them apart. Classical physics would suggest that protons need enough energy to overcome this repulsive barrier directly. In other words, they would have to slam together with enough speed to climb over the electromagnetic hill between them. The sun's core is hot and some protons do move very quickly, but not enough of them have the energy required for fusion to happen easily by classical reasoning alone. If classical physics were the whole story, the sun would struggle to produce energy at the rate we observe. It might be a much dimmer, much less interesting object, which would be inconvenient for plants, weather, oceans, breakfast, and almost everything else that has become fond of existing. Quantum tunneling changes the situation. Because protons are quantum objects, they are not described as tiny hard marbles with perfectly definite paths. They have wave-like properties, and their behavior is described through quantum probabilities. When two protons approach the barrier created by their electric repulsion, they do not always need to climb over it in the classical sense. Their wave functions can extend into the region that classical physics would call forbidden. Most of the time, they still do not fuse. Most proton collisions in the sun fail. The particles approach, repel, and move apart again. But occasionally quantum tunneling allows two protons to get close enough for the strong nuclear force to act. The probability for any one collision is small, but the sun contains an enormous number of protons, all moving and colliding in its dense core. Across that vast population, rare quantum successes happen often enough to matter. The sun does not need every collision to produce fusion. It only needs enough of them to succeed steadily over time. The main fusion process in the sun is called the proton-proton chain. In broad terms, hydrogen nuclei are gradually converted into helium nuclei through a sequence of nuclear reactions. Along the way, energy is released, along with particles such as positrons and neutrinos. The energy eventually makes its long journey outward through the sun, interacting with matter again and again before emerging from the surface as sunlight. The light reaching Earth began with processes deep in the solar core, where gravity, heat, nuclear forces, and quantum tunneling all work together. The proton-proton chain is essential because it explains how a star like the sun can shine for billions of years. Hydrogen is the sun's main fuel, and helium is the main product of that fusion. A small amount of mass is converted into energy, following the principle associated with Albert Einstein's special relativity. Energy equals mass multiplied by the speed of light squared. That energy supports the sun against gravitational collapse and provides the light and heat that make Earth's surface habitable. The question of what powers the sun was once a major scientific puzzle. In the 19th century, ordinary chemical burning could not explain the sun's enormous energy output over geological timescales. Gravitational contraction could provide more energy than chemistry, but still not enough to match the vast age of Earth implied by geology and biology. In the early 20th century, Arthur Eddington argued that the Sun might be powered by the conversion of hydrogen into helium, connecting stellar energy to nuclear physics before the full details were known. Later, Hans Bethe worked out key nuclear processes that power stars, including the proton-proton chain and the carbon-nitrogen-oxygen cycle. His work helped turn the idea of stellar fusion from a broad insight into a detailed scientific framework. The Sun was no longer simply a glowing ball in the sky. It became a nuclear furnace, held together by gravity, regulated by pressure, and quietly assisted by the strange probabilities of quantum mechanics. Quantum tunneling is crucial to that picture. It does not make fusion easy in the casual sense. The Sun's core is still a place of extreme heat and pressure, and the fusion rate is carefully limited by the difficulty of getting protons close enough to react. In fact, this slowness is part of why the Sun lasts so long. If fusion happened too easily, the Sun would burn through its fuel far faster. The faint difficulty of proton tunneling helps give the Sun its long, steady lifetime. There is something quietly astonishing about that. The same kind of quantum behavior that allows an alpha particle to escape from a nucleus also helps protons in the Sun overcome their mutual repulsion. In one case, tunneling lets something leave a nuclear trap. In another, it lets particles come close enough to bind together. Different settings, different details, but the same deeper principle. Quantum probability allows processes that classical barriers would strongly suppress. This means ordinary daylight is not ordinary at all. Every patch of sunlight on a windowsill carries the distant consequence of quantum events in the solar core. The warmth on skin, the growth of leaves, the movement of weather, and the shimmer of morning light all trace back to particles doing something that would seem impossible if nature were only classical. The Sun does not shine because quantum physics is magical. It shines because quantum physics is real, precise, and woven into the rules governing matter at small scales. Tunneling is not an exception to the universe's order. It is part of that order. And so the sunlight arriving quietly at Earth is not just heat from a distant star. It is a message from the strange world beneath ordinary reality, where barriers are not always absolute, where probability can become power, and where a tiny chance repeated across a star can help illuminate an entire planet. Quantum tunneling is not only something that happens in the hidden centers of atoms or the bright core of the Sun, it is also part of the quiet machinery of modern technology. The same strange rule that helps an alpha particle escape a nucleus and helps protons fuse inside a star can also be found inside devices made by human hands. In a rather calm but slightly suspicious way, the quantum world has been helping run everyday life from behind the scenes. This is one of the most important things to understand about quantum physics. It is not just a collection of exotic ideas kept safely inside university lecture halls, where equations roam freely and coffee cups slowly gather around tired physicists. Quantum behavior is engineered, controlled, measured, and used. It lives inside electronics, sensors, memory devices, and some of the most advanced research technologies being built today. The strangeness is not decorative. It works. One early and important example is the tunnel diode. A diode is an electronic component that usually allows electric current to flow more easily in one direction than the other. Ordinary diodes are extremely common in electronics. A tunnel diode is different because it uses quantum tunneling directly. It is made with semiconductor materials arranged so that electrons can tunnel through a very thin energy barrier. This creates unusual current behavior. In a normal electronic component, increasing voltage often increases current in a fairly straightforward way, at least over a useful range. But in a tunnel diode, there can be a region where increasing the voltage actually causes the current to decrease. This is called negative resistance. Though the phrase sounds as if the diode is refusing to cooperate out of principle, in reality it comes from the way available quantum states line up inside the semiconductor. When the states are aligned, electrons tunnel readily. When the alignment shifts, tunneling becomes less likely, and the current drops. Tunnel diodes were especially important in early high-speed electronics, because tunneling can happen extremely quickly. They showed that quantum effects were not just strange observations, but practical tools. Engineers could take a rule that seems almost impossible from an everyday perspective and turn it into a useful behavior in a circuit. The barrier was not being ignored, it was being used. Another familiar technology shaped by tunneling is flash memory. Flash memory is the kind of memory found in devices such as USB drives, memory cards, solid-state drives, phones, tablets, and many other forms of portable electronics. It stores information without needing constant power, which is why a file can remain safely tucked away even after a device has been switched off. Quietly heroic behavior, really. Not dramatic, but very useful. In broad terms, flash memory works by storing electric charge in tiny structures inside a semiconductor device. In many designs, electrons are placed onto or removed from a floating gate or charge trapping layer. To get there, they must pass through an extremely thin insulating layer. Classically, an insulator is supposed to resist the flow of charge. But if the insulating barrier is thin enough, electrons can tunnel through it under controlled conditions. Engineers apply voltages that make tunneling likely when information needs to be written or erased, and unlikely when the information needs to remain stored. The details of modern flash memory are complex and the designs have changed over time, but the broad idea is beautifully quantum. Information can be stored because electrons are guided into states where they remain trapped, and tunneling is used to move them across barriers when needed. The same principle that sounds so strange in a physics lesson becomes part of saving photographs, documents, messages, and the small digital clutter of modern life. Somewhere in the device, electrons are being gently persuaded to do what classical intuition would not expect. An even more delicate example comes from Josephson junctions. In the early 1960s, Brian Josephson predicted that electric current could tunnel between two superconductors separated by a very thin insulating barrier. A superconductor is a material that can carry electric current without ordinary electrical resistance when cooled below a certain temperature. In a Josephson junction, the two superconducting regions are separated by a barrier so thin that quantum tunneling can connect them. This prediction was remarkable because it involved not just single particles tunneling in isolation, but a collective quantum state extending across the junction. The current can flow through the barrier without an applied voltage in a way now known as the Josephson effect. It is one of the clearest examples of quantum mechanics appearing at a scale large enough to be engineered into devices, though still under very controlled and often extremely cold conditions. Josephson junctions are important in several areas of modern science and technology. They are central to superconducting circuits, where quantum behavior can be controlled with great precision. They appear in devices known as superconducting quantum interference devices, often called SQUIDs, which are among the most sensitive magnetic field detectors ever made. These instruments can detect incredibly tiny changes in magnetic fields, and are used in physics, materials science, geology, and some medical research. Josephson junctions are also important in some quantum computing designs. In superconducting quantum computers, carefully designed circuits use Josephson junctions to create artificial quantum systems that can behave as qubits. A qubit is a quantum unit of information, and unlike an ordinary bit, it must be understood through quantum states, measurement, and probability. The engineering is extremely difficult, because quantum systems are fragile and easily disturbed by their surroundings. But the very fact that such machines can be built at all shows how far quantum physics has moved from abstract theory into practical design. This does not mean every modern device is secretly a quantum computer, or that quantum physics is doing mystical acrobatics inside every appliance. The point is more grounded and more impressive. The small-scale structure of matter obeys quantum rules, and modern technology often works because scientists and engineers have learned to shape those rules into reliable tools. Sometimes that means using semiconductors. Sometimes it means controlling tunneling through thin barriers. Sometimes it means cooling circuits until superconducting quantum effects become visible and useful. Tunneling makes this especially clear because it turns an impossible-sounding event into a controllable process. In nuclei, it explains radioactive escape. In stars, it helps fusion occur. In electronics, it can guide currents, store memory, and create sensitive quantum devices. The same basic idea appears again and again in very different settings, like a quiet signature written through nature and technology. So quantum strangeness is not sealed away in the remote parts of reality. It is not only inside stars, particle accelerators, or philosophical arguments about measurement. It is built into the modern world, hidden in the small components that make larger systems feel smooth, ordinary, and dependable. The device may look simple from the outside: a phone, a memory card, a circuit board, a sensor. But beneath that plain surface, matter is obeying rules that would have shocked classical physics. Barriers are crossed by probability. Currents flow through forbidden gaps. Information is held by tiny arrangements of charge. And the strange world of quantum physics quietly becomes part of everyday life, without ever needing to announce itself. For a long time, atoms were real in theory before they were visible in anything like a direct way. Scientists could infer them from chemistry, from gases, from crystals, from radiation, from the way matter behaved when measured carefully. The evidence became overwhelming. Atoms were not imaginary dots invented to make equations feel busy. They were the hidden structure of matter. But actually seeing their arrangement on a surface, tracing the landscape of atoms one by one, required something far stranger than an ordinary microscope. A normal optical microscope uses light. That works beautifully for many things, from cells to tiny crystals to the general drama of whatever is living in pond water. But visible light has a wavelength much larger than an individual atom. That means it cannot resolve atomic details in the same straightforward way a magnifying glass can reveal the fibers in paper or the delicate structure of a leaf. To study atoms, science needed tools that did not depend on ordinary vision. One of the most remarkable of those tools is the scanning tunneling microscope. It is one of the clearest and most visually powerful demonstrations of quantum tunneling in modern science, because it turns tunneling from a hidden probability into something that can be used to map the surface of matter. It does not simply tell scientists that quantum tunneling exists. It uses tunneling as a kind of ultra-sensitive touch, allowing the shape of a surface to be traced at atomic scales. The scanning tunneling microscope was developed in the early 1980s by Gerd Binnig and Heinrich Rohrer at IBM Zurich. Their work was important enough that they later received the Nobel Prize in Physics. It opened a new way of studying surfaces, atoms, and materials, not by imagining what atoms might be doing from far away, but by using quantum behavior to examine the fine details of a surface with extraordinary precision. The basic idea is beautifully delicate. A sharp conducting tip is brought extremely close to a conducting or semiconducting surface. The tip does not scrape across the surface like a needle on a record. It is held incredibly near, often only about the width of a few atoms away. Between the tip and the surface there is a tiny gap, and classically, electrons should not simply pass through empty space across that gap, unless they have enough energy to do so. But because electrons are quantum objects, their wave functions can extend into the gap. If the tip is close enough, electrons can tunnel between the surface and the tip. That tunneling creates a small electric current. The current depends very sensitively on the distance between the tip and the surface. If the tip moves even slightly closer, the tunneling current can increase strongly. If it moves slightly farther away, the current can drop sharply. This sensitivity is the secret of the instrument. The scanning, tunneling microscope does not need to physically bump into atoms. It can feel changes in the surface through the tunneling current, like reading tiny hills and valleys, by noticing how easily electrons cross the gap. In one common mode of operation, the microscope moves the tip across the surface while adjusting its height to keep the tunneling current constant. If the surface rises because an atom is beneath the tip, the instrument pulls the tip back slightly. If the surface dips, the tip moves closer. By recording those tiny movements, the microscope builds a map of the surface. The result can show atomic scale structure with extraordinary clarity. It is not a photograph in the everyday sense, but it can reveal where atoms are arranged on a surface in a way that feels almost like seeing the invisible become visible. This changed the study of materials. Before instruments like the scanning, tunneling microscope, scientists had many powerful ways to infer atomic arrangements, especially through methods such as X-ray crystallography and electron microscopy. Those methods remain extremely important, but the scanning tunneling microscope gave researchers a new kind of access to surfaces. It allowed them to study individual atoms, defects, steps, patterns, and electronic structures at scales that had once felt unreachable. Surface physics benefited enormously because surfaces are not just the outside of materials. They are places where atoms behave differently from atoms buried deep inside a solid. Surface atoms have fewer neighbours. Their bonds, energies, and electron behaviour can change. This matters for catalysts, semiconductors, corrosion, crystal growth, nanostructures, and many processes that happen where one material meets another. The surface is where matter often negotiates with the world around it, and the scanning tunneling microscope gave science a way to listen closely to that negotiation. It also helped launch and shape nanoscience. Nanoscience deals with structures measured in nanometers, where a nanometer is 1/1000th of a meter. At that scale, the arrangement of individual atoms and molecules can strongly affect the properties of a material. A tiny change in structure may alter conductivity, magnetism, chemical reactivity, or optical behavior. The scanning tunneling microscope did not just let scientists observe these features. In some cases, it also allowed them to manipulate atoms on surfaces, moving individual atoms under carefully controlled conditions. This is not quite the universe handing out a set of atomic tweezers, but it is impressively close for something that began as a piece of quantum measurement equipment. The deeper point is that tunneling became a tool for seeing. That is a strange and wonderful reversal. Earlier, tunneling appeared as something that allowed alpha particles to escape nuclei or protons to get close enough for fusion in the sun. It seemed like a hidden mechanism inside nature. With the scanning tunneling microscope, the same effect becomes part of human perception, extended through technology. Quantum probability is transformed into an instrument for mapping reality. There is something quietly poetic about that. The microscope does not see atoms by flooding them with light in the ordinary way. It senses them through a tiny current made possible by the fact that electrons do not behave like little marbles. The instrument works precisely because the quantum world is not classical. The very strangeness that once made particles seem difficult to understand becomes the reason atoms can be studied so closely. So the scanning tunneling microscope is more than a clever device. It is a reminder that quantum physics is not only about what nature hides, it is also about what nature allows us to reveal. A barrier that would be absolute in classical thought becomes a bridge for electrons. A tiny gap becomes a measuring tool. A surface that once had to be inferred becomes a landscape of atomic detail. And through that delicate current, flowing across a space too small for ordinary imagination, quantum tunneling lets science feel the shape of matter itself. Once quantum tunneling has been introduced, one question tends to arrive almost immediately, with the innocent persistence of a cat near a closed door. If particles can sometimes cross barriers they should not classically be able to cross, then why can people not walk through walls? It is a fair question. In fact, it is exactly the kind of question quantum physics invites, because tunneling sounds so much like a loophole in reality. If an electron can pass through a barrier, and an alpha particle can escape a nucleus, and protons in the sun can tunnel close enough for fusion to happen, then perhaps a person could, in principle, tunnel through a wall as well. The answer is subtle, but also reassuring for anyone who would prefer architecture to keep doing its job. Quantum physics does not say that walking through walls is practically possible. It says that the basic rules of matter are probabilistic at small scales. For tiny particles, under the right conditions, tunneling probabilities can be large enough to matter. For large everyday objects, those probabilities become so unimaginably small that they are physically irrelevant. Not just unlikely in the way rain is unlikely on a clear day. Not even unlikely in the way finding one particular grain of sand on a beach would be unlikely. The probability becomes so tiny that ordinary language begins waving a little white flag. The reason begins with mass. Tunneling is much easier for very light particles such as electrons, because their quantum wave-like behavior can spread in ways that make barriers less absolute. Heavier objects have much shorter associated wavelengths under ordinary conditions, and their wave functions do not extend through barriers in any useful way. An electron can have a meaningful chance of tunneling across a very thin insulating layer. A person approaching a wall does not have a meaningful chance of tunneling through it, even with a positive attitude and excellent posture. Then there is complexity. A human body is not one simple particle. It is made of an enormous number of atoms arranged into molecules, cells, tissues, organs, and all the complicated biological arrangements required for breathing, thinking, blinking, digesting, and occasionally wondering whether quantum physics is being deliberately difficult. For a whole person to tunnel through a wall, it would not be enough for one electron or one atom to appear on the other side. The entire body would have to tunnel together in a coordinated way, preserving the arrangement of every particle closely enough that the person remains a person. That coordination is the real problem. The atoms in the body are constantly interacting with one another. They're also interacting with air molecules, light, heat, clothing, the floor, and the wall itself. These interactions do not leave the body as a clean, isolated quantum system. They constantly entangle it with its surroundings in a messy, ordinary, warm environment. At human scales, the delicate quantum possibilities that are important for small, isolated systems become washed into a stable-looking classical world. This process is known as decoherence. Decoherence is the process by which a quantum system loses visible quantum behavior through interaction with its environment. It does not mean that quantum physics stops being true. The underlying world is still quantum, but the clear, delicate features that allow superposition, interference, and other quantum effects to be observed become effectively unavailable when a system becomes strongly entangled with its surroundings. The physicist Wojciech Zurek has been especially important in developing the modern understanding of decoherence and the emergence of classical-looking reality from quantum foundations. Decoherence helps explain why large objects do not appear to exist in obvious mixtures of different states, and why the world around us seems definite, stable, and classical. It shows how the ordinary world can emerge from quantum rules without needing every object to behave like an isolated electron in a laboratory. Temperature also matters. Everyday objects are warm, and warmth means internal motion. The atoms and molecules inside a human body are jiggling, colliding, rotating, vibrating, and exchanging energy. This thermal activity makes delicate quantum coordination even harder to maintain. In laboratories, many quantum effects are easiest to observe when systems are cooled, isolated, and carefully protected from outside disturbance. A person in a room is none of these things. A person is a warm, complicated, noisy quantum system, which is a lovely description biologically, but a terrible setup for coherent tunneling through masonry. The number of particles makes the situation even more extreme. If a single particle has a small chance of tunneling through a barrier, a large object would require an astronomical number of particles to behave together in just the right way. The probability of that combined event drops beyond any realistic meaning. It is not merely that nobody has waited long enough. It is that the timescale involved would dwarf any practical or cosmic patience. The universe is old, but it is not that indulgent. This is why quantum physics must be handled carefully. It does not mean anything imaginable can happen in ordinary life. It means that nature assigns probabilities to outcomes according to quantum rules. Some probabilities are large enough to observe. Some are small but still important across huge numbers of particles or long periods of time. Others are so close to zero that they never show up in the everyday world. A possibility can exist mathematically while being physically irrelevant in practice. That distinction protects quantum physics from becoming nonsense. Tunneling does not turn walls into optional suggestions. It does not mean chairs might suddenly pass through floors, or that cups of tea might drift through tables, though the tea would probably enjoy the drama. The familiar world is stable because large objects are massive, complex, warm, and constantly interacting with their environments. Their quantum nature has not vanished, but it has become hidden beneath the behavior we call classical. In this way, tunneling leads to a deeper question. Why does the world look so ordinary when its foundations are so strange? Why do atoms obey quantum rules, while tables, planets, and people seem to follow the calmer habits of classical physics? Decoherence is one major part of that answer. Scale, mass, temperature, and interaction all help turn quantum possibilities into the reliable world of definite objects. So walking through walls remains safely unavailable. The quantum world does allow barriers to be crossed in surprising ways, but only under conditions that belong mostly to tiny particles, thin barriers, and carefully prepared systems. For human bodies, walls remain walls, and perhaps that is comforting. The universe is strange enough to let particles tunnel through forbidden barriers, but stable enough that a sleepy person can lean against a wall and trust it not to become a philosophical disagreement. Quantum tunneling shows that the small world does not treat barriers in the same simple way as classical physics. But tunneling is only one part of a larger shift. Quantum physics does not merely change what can happen, it also changes what can be known. At the smallest scales, nature does not always allow every property of a system to be pinned down with unlimited sharpness. The world is not simply hiding details from careless observers. The limits appear to be built into the structure of quantum reality itself. This idea is most famously expressed through Heisenberg's uncertainty principle. Werner Heisenberg introduced this principle in the late 1920s during the intense early development of quantum mechanics. It is one of the most widely known ideas in modern physics, and also one of the easiest to misunderstand. In everyday language, uncertainty often means confusion, lack of information, or an instrument that is not quite good enough. A blurry photograph is uncertain because the camera shook. A weather forecast is uncertain because the atmosphere is complicated. A person looking for their keys is uncertain because the keys have once again entered their mysterious domestic migration cycle. Quantum uncertainty is different. Heisenberg's uncertainty principle says that certain pairs of properties cannot both be known with unlimited precision at the same time. The most famous pair is position and momentum. Position tells where something is. Momentum describes how much motion it has, depending on both its mass and its velocity. In classical physics, there is no deep reason why an object cannot have both a perfectly definite position and a perfectly definite momentum. A tennis ball flying through the air can be imagined as being at one exact place, while moving with one exact speed in one exact direction. For quantum objects, that picture breaks down. The more precisely a particle's position is defined, the less precisely its momentum can be defined. The more precisely its momentum is defined, the less sharply its position can be pinned down. This is not simply because the measuring equipment is clumsy. It is not that the electron is very small and the laboratory has misplaced the good ruler. It arises from the wave-like nature of quantum systems. A useful comparison is a wave in sound or water, though the quantum wave function is not literally either of those things. A wave that is spread out smoothly over a long distance can have a well-defined wavelength, but because it is spread out, it is not sharply located in one place. A short, sharply localized wave pulse can be placed more clearly, but it must be made from a mixture of different wavelengths. In quantum mechanics, wavelength is connected to momentum, so a particle described by a very spread-out wave function can have a more definite momentum, while a particle squeezed into a small region must involve a wider range of possible momenta. This is the root of uncertainty. It comes from the structure of waves and from the way quantum objects are described, not merely from human ignorance. The wave function does not behave like a filing cabinet containing hidden classical facts that would all be neatly visible if only someone opened the correct drawer. It gives a different kind of description, one where certain properties are linked in such a way that sharpening one necessarily blurs the other. This helps make tunneling more understandable. A particle trapped in a small region is not like a marble sitting motionless in a box. The more tightly it's confined, the less sharply its momentum can be defined. Its wave function is shaped by the boundaries around it, and it can extend into regions that would be forbidden in a purely classical description. When a particle faces a barrier, quantum mechanics does not describe it as a little object arriving at the wall with one exact path and one exact fate. It describes a wave function meeting a barrier, partly reflected, partly extending into it, and sometimes leaving a small probability beyond it. Uncertainty also plays a major role in the structure of atoms. In older pictures, electrons were imagined as tiny planets orbiting a nucleus, but that image cannot be right. If electrons were simply little charged particles circling in classical paths, atoms would be unstable in ways that ordinary matter clearly is not. Quantum mechanics replaces those tiny orbits with electron orbitals, which are probability distributions shaped by the wave function. An electron in an atom does not have one neat little track around the nucleus. It occupies a quantum state with a spread of possible positions and momenta governed by the rules of quantum mechanics. This is not a minor detail. It helps explain why atoms have size, structure, and stability. If an electron was squeezed directly into the nucleus, its position would become extremely confined. The uncertainty principle then implies a very large spread in momentum, which is associated with a large kinetic energy. In simpler terms, confining the electron too tightly becomes energetically costly. Quantum uncertainty helps prevent electrons from simply collapsing into nuclei. Along with the electromagnetic force and the allowed quantum states of atoms, it helps make stable matter possible. Electron clouds, then, are not clouds because scientists are being vague. They're probability distributions. They show where electrons are likely to be found if measured. Different orbitals have different shapes and energies, and these shapes help determine how atoms bond, how molecules form, how chemistry works, and why matter has the properties it does. The solidity of a table, the transparency of glass, the color of a mineral, and the structure of a protein all ultimately depend on quantum rules that do not resemble tiny marbles circling in tidy mechanical loops. Heisenberg's uncertainty principle is therefore not just a philosophical curiosity, it is part of the reason matter behaves as matter. It limits the old dream of perfect classical knowledge, where everything has a precise position, a precise motion, and a future that could be calculated exactly if only enough details were known. Quantum physics does not allow that complete classical picture. It gives precision of a different kind, built from probabilities, wavefunctions, and relationships between measurable properties. This does not mean knowledge becomes useless, quite the opposite. Quantum mechanics is one of the most successful scientific theories ever created. It predicts atomic spectra, chemical behavior, semiconductor physics, lasers, magnetic resonance imaging, and many other phenomena with extraordinary accuracy. The uncertainty principle does not make science weaker. It makes science more honest about the kind of world being described. The deeper strangeness is that the limit is not only practical, it is not merely that instruments disturb what they measure, though measurement can certainly disturb quantum systems. The deeper point is that quantum properties do not all exist together in the same, sharply defined classical way. Nature seems to resist being reduced to a perfectly detailed mechanical snapshot. So quantum physics changes the meaning of knowing. It does not say reality is unknowable. It says reality is knowable through rules that are subtler than ordinary intuition expects. Position and momentum, particle and wave, certainty and probability, barrier and possibility all begin to shift. The world remains lawful, but the laws are not built for human common sense. At the smallest scales, nature is not simply waiting to reveal a hidden marble with a hidden path. It offers a wave function, a pattern of possible outcomes, and a limit on how sharply certain questions can be answered together. The strange world of quantum physics is not strange because it has no rules. It is strange because even knowledge has rules. Superposition is one of the most famous ideas in quantum physics, and also one of the easiest to make sound more mysterious than it needs to be. It is often described as a particle being in two places at once, or an object being in many states at the same time. Those phrases can be useful as a first doorway, but they can also become misleading very quickly. Superposition is not a magical permission slip for ordinary objects to do whatever they like. It is a precise feature of quantum theory, rooted in the wave function and in the way possible outcomes are represented before measurement. In quantum mechanics, a system can be described as a combination of possible states. That combination is called a superposition. Before a definite measurement outcome is found, the quantum state may contain several possibilities at once, each contributing to what may later be observed. The important word is described. Superposition is not simply a tiny object making up its mind in a dramatic personal crisis. It is the mathematical description of a quantum system before a particular measurement forces one definite result to appear. A simple example is electron spin. Spin is a quantum property that behaves in some ways like angular momentum, although it should not be imagined too literally as an electron spinning like a miniature planet. When measured along a chosen direction, an electron spin can produce one of two possible outcomes. Before that measurement, the electron can be in a superposition of those possible spin states. Quantum theory does not describe it as secretly having one ordinary answer all along in the classical sense. Instead, The wave function gives probabilities for the outcomes that may be found. Another example comes from photon polarization. Polarization describes the orientation of light's electromagnetic vibration. A photon can be prepared in a state that is not simply one definite polarization relative to a later measurement, but a superposition of possible polarization outcomes. When it is measured, one result is found. Before measurement, the quantum state contains the structure needed to predict the probabilities of those results. This is not because the photon is indecisive. Photons do not have tiny meetings with themselves. It is because the quantum description is built differently from the everyday picture of a thing having all its properties sharply settled in advance. Atomic energy states offer another important example. An atom can occupy particular allowed energy levels, and under certain conditions it can be placed in a superposition of different energy states. This matters in atomic clocks, spectroscopy, lasers, and many precision experiments. The electron in an atom is not simply hopping between little shelves in a mechanical cupboard. Its behavior is described by quantum states, and superpositions of those states can produce interference effects, transitions, and measurable patterns with extraordinary accuracy. The strange part is that superposition is not just ignorance. If a card is placed face down on a table, it may be either red or black, and a person may not know which. But in the ordinary world, the card already has a definite colour. The uncertainty is only in the observer's knowledge. Quantum superposition is different. The theory treats the system as being in a genuine combination of possible states before measurement, and experiments involving interference show that these possibilities can affect one another. They are not merely hidden labels waiting to be read. Still, it is important not to stretch this idea too casually into the everyday world. Saying that an electron can be in a superposition of spin states does not mean a chair is casually both in the room and in the garden in any useful everyday sense. Large objects are made of enormous numbers of particles, constantly interacting with air, light, heat, floors, walls, and themselves. These interactions rapidly destroy the kind of delicate quantum coherence needed for obvious superposition effects. This is where decoherence becomes important again. The underlying reality is still quantum, but the visible behavior of large warm objects becomes stable and classical looking. This was part of the point behind Schrödinger's cat. Erwin Schrödinger introduced the famous cat thought experiment in 1935, not as a cheerful suggestion for laboratory animal care, but as a critique of applying quantum ideas too simply to large familiar objects. In the thought experiment, a cat is placed in a sealed box with a quantum event that may or may not trigger a deadly mechanism. If the quantum event is treated as a superposition, then the cat seems to become entangled with that superposition, leading to the strange phrase that the cat is both alive and dead until observed. Schrödinger's point was not that cats normally behave this way, it was that something puzzling happens when quantum rules are extended from tiny systems to everyday objects without explaining where the ordinary definite world comes from. The thought experiment exposes the measurement problem, the question of how and why definite outcomes arise from quantum possibilities. It is less a cute story about a cat, and more a very serious complaint wearing whiskers. Superposition also connects directly to tunneling. In tunneling, a particle approaching a barrier is not described as a little marble following one fixed path. Its wave function contains the possibilities allowed by quantum mechanics. Part of the wave function may be reflected, while part may extend into the barrier and, under the right conditions, beyond it. The particle's behavior is shaped by a quantum state that includes possible outcomes rather than one classical route. Tunneling and superposition both reveal the same deeper lesson. Before measurement, quantum physics often gives a structured landscape of possibility, not a single familiar story. This does not make quantum theory weak or vague. It is exactly the opposite. The probabilities predicted from superpositions can be tested with remarkable precision. Interference experiments, atomic spectra, quantum optics, magnetic resonance, and modern quantum information science all rely on the fact that superposition is not just a philosophical curiosity. It is a working principle of nature. Yet the interpretive questions remain. What exactly is the wave function? What counts as a measurement? Why does one outcome appear when several possibilities were present in the quantum description? Different interpretations of quantum mechanics offer different answers, including the Copenhagen interpretation, many worlds interpretations, pilot wave theory, and objective collapse models. The experiments agree with the predictions, but the meaning behind those predictions is still debated. Superposition, therefore, sits at the heart of the strange world of quantum physics. It shows that matter and light are not built from little objects carrying a full set of ordinary properties in advance. They are described by quantum states, by combinations of possibilities, and by probabilities that become definite only when the right kind of measurement is made. Reality is not vague. It is not lazy. It's not shrugging. It is simply written in a language where possibility can be real enough to interfere with itself before the world gives one clear answer. Quantum physics becomes especially strange when it moves from what might happen to what is actually found. Before measurement, the theory often gives a spread of possible outcomes described by the wave function. After measurement, only one outcome appears. An electron is detected here, not there. A photon passes this way, not that way. A detector clicks in one place, while the other possible clicks remain unrealized. Somewhere between the quiet mathematics of possibility and the definite fact of observation lies one of the deepest unresolved questions in quantum mechanics. This is known as the measurement problem. The measurement problem asks why quantum theory seems to describe systems one way before measurement and another way afterward. Before measurement, a quantum system can be in a superposition of possible states, with probabilities attached to different outcomes. The wave function evolves smoothly according to the Schrödinger equation. But when a measurement is made, the result is definite. The instrument records one value. The screen shows one mark. The world does not seem to display all the possibilities at once, at least not in ordinary experience. This is not just a small technical nuisance. It touches the question of what the wave function actually represents. Is it a real physical thing? Is it a description of knowledge? Is it a tool for calculating probabilities? Does measurement cause a real physical change, or does it only update what can be said about the system? Quantum mechanics predicts experimental results with astonishing success, but the meaning of measurement remains one of its most persistent conceptual puzzles. Niels Bohr was one of the central figures in the early interpretation of quantum mechanics. Along with Werner Heisenberg and others, Bohr helped shape what became known as the Copenhagen interpretation. This is not one perfectly fixed doctrine, despite the way it is sometimes presented. It is better understood as a family of related ideas developed around Bohr's view that quantum systems should be described in terms of experimental arrangements and observable outcomes. In the Copenhagen tradition, the wave function is often treated as a way of calculating probabilities for measurement results, rather than as a simple physical wave sitting in space like water or sound. The act of measurement plays a special role because it is when a definite outcome becomes part of the description. Bohr emphasized that the measuring apparatus and the conditions of observation matter deeply. What can be said about a quantum system depends on how the question is asked. This does not mean that human consciousness magically creates reality. That idea is often attached to quantum physics in popular culture, usually with the confidence of someone selling either a book, a crystal, or a very expensive weekend retreat. In mainstream physics, measurement does not require a human mind staring meaningfully at a particle. A detector, a photographic plate, an atom, an environment, or another physical system can become involved in producing a record. The key issue is not consciousness, but physical interaction, information, and the transition from quantum possibility to definite outcome. One of the clearest demonstrations of this strange relationship is the double-slit experiment. In its simplest form, particles such as photons or electrons are sent toward a barrier with two narrow openings, and a screen behind the barrier records where they arrive. If both openings are available and no measurement is made to determine which opening each particle passes through, an interference pattern can build up on the screen. This pattern is wave-like. It shows regions where arrivals are more likely, and regions where they are less likely, as if the possible paths are interfering with one another. The truly strange part is that this can happen even when particles are sent one at a time. Each particle is detected as a single event on the screen, a tiny definite mark. But after many particles have arrived, the overall pattern reveals interference. Quantum theory describes this through a wave function that includes both possible paths. The particle is not simply acting like a classical marble choosing one slit while secretly ignoring the other. The possibilities themselves contribute to the final probability pattern. But if a measurement is made to determine which slit the particle goes through, the interference pattern disappears. The screen no longer shows the same wave-like distribution. Instead, the results become more like particles passing through one opening or the other. The act of gaining which path information changes what can be said about the quantum system. It changes the available description of the possibilities, and therefore the pattern of outcomes. This is where measurement becomes more than passive looking. In ordinary life, seeing where a football goes does not usually change whether it went left or right. The ball had a path, and observation merely reveals it. In quantum physics, the measurement arrangement helps define which properties are being asked about. Asking for path information is not the same as allowing interference between paths. Nature does not always provide every classical detail at once. It answers the question the experiment is built to ask. That is why quantum measurement is so unsettling. It suggests that physical facts at the smallest scales may not exist in the same straightforward way imagined by classical physics. This does not mean reality is imaginary. It means that properties such as position, momentum, path, spin, and polarization are tied to the conditions under which they are measured. A quantum system is not always carrying a complete set of definite classical answers before the experiment begins. Different interpretations of quantum mechanics respond to this puzzle in different ways. The Copenhagen interpretation accepts the special role of measurement, while remaining cautious about what can be said beyond observed outcomes. The many worlds interpretation treats all possible outcomes as realized in a branching universal wave function. Pilot wave theory proposes that particles have definite positions guided by an underlying wave. Objective collapse theory suggests that wave functions physically collapse under certain conditions. These interpretations differ deeply, yet many lead to the same tested predictions in ordinary quantum experiments. So the measurement problem remains open not because quantum theory fails, but because it works so well while leaving a strange question behind. It gives probabilities before measurement and definite outcomes after measurement. It tells science how to calculate what will be observed, but still leaves room to ask what the wave function really means. The strange world of quantum physics is therefore not only about particles crossing barriers, waves behaving like matter, or matter behaving like waves. It is also about what counts as a fact. A measurement is not merely a glance. It is a physical event that helps turn a landscape of possible outcomes into the one result that becomes part of the world. And that may be the quietest strangeness of all. Reality does not always seem to arrive fully written in advance. Sometimes, at the quantum scale, it appears to become definite only when nature is asked a question carefully enough to answer. Separateness feels obvious in ordinary life. One object is here, another is there. A cup on a table is not the same thing as a lamp across the room. Two stones can be carried in opposite directions, placed in different countries, or left on different planets, and common sense says each one has its own private state. What happens to one should not instantly define what is true about the other. Distance, in everyday experience, is a reliable kind of separation. Quantum physics makes that idea more delicate. Quantum entanglement is the situation in which two or more quantum systems must be described together, even when they are far apart. Their property is not fully independent in the way classical intuition expects. The combined system has one shared quantum description, and measurements made on one part can be strongly correlated with measurements made on the other. The systems may be separated by a laboratory bench, a city, or in principle much greater distances, yet the quantum state linking them cannot always be reduced to two separate little stories. This does not mean the particles are communicating like tiny messengers, racing through space with urgent envelopes. It means their quantum state was created or arranged in such a way that the properties measured later are connected by the rules of quantum mechanics. The connection is not a signal travelling between them in the ordinary sense. It is deeper and stranger than that, which is precisely why entanglement has unsettled physicists for so long. The concern was made famous in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. Their argument, often called the Einstein-Podolsky-Rosen argument, was designed to show that quantum mechanics might be incomplete. They considered situations where two particles interact and then move far apart, while remaining described by a shared quantum state. According to quantum theory, measuring one particle can let an observer predict the corresponding property of the other particle, even though it is distant. Einstein was troubled by this. He did not like the idea that a measurement in one place could seem to have an immediate connection with the description of something far away. He famously objected to what he called spooky action at a distance. His discomfort was not a refusal to accept evidence because it felt weird. Einstein had helped create quantum theory through his work on light quanta and the photoelectric effect. His objection was more precise. He believed that physical reality should be local, meaning that influences should not travel faster than light, and that distant objects should have their own definite properties independent of how they are measured elsewhere. The Einstein-Podolsky-Rosen argument raised a serious question. Were quantum particles really connected in this strange non-classical way? Or did they carry hidden information that quantum mechanics simply did not describe? Perhaps the theory worked statistically, but beneath it, there might be a deeper classical layer, with hidden variables quietly determining the outcomes in advance. That possibility was tempting, because it would restore a more familiar kind of separateness. Then came John Bell. In the 1960s, John Bell developed Bell's theorem, one of the most important results in the foundations of physics. Bell showed that the disagreement between quantum mechanics and certain local hidden variable theories was not merely philosophical. It could be tested experimentally. If particles carried pre-existing local instructions, the correlations between distant measurements would have to obey certain limits, now called Bell inequalities. Quantum mechanics predicted that entangled particles could violate those limits. This transformed the debate. It was no longer only a question of taste, interpretation, or philosophical preference. Nature could be asked. Experiments later showed that quantum predictions were right. Alain Aspect and his collaborators carried out influential Bell test experiments in the early 1980s, measuring correlations between entangled photons and finding results consistent with quantum mechanics rather than simple local hidden variable expectations. Later experiments improved the methods and closed important loopholes, including tests involving more efficient detectors, better separation between measurement choices, and stricter timing conditions. These loophole-reduced Bell tests strengthen the evidence that nature does not fit the simplest local realistic picture Einstein had hoped might survive beneath quantum theory. This is one of the most remarkable conclusions in modern science. The universe appears not to be built from separate little objects carrying complete sets of local properties in the classical way. At least for entangled systems, the whole cannot always be understood as merely the sum of independent parts. The shared quantum state matters. But this must be said carefully. Entanglement does not allow faster-than-light messaging. It does not let someone send a usable signal instantly across space. When one observer measures an entangled particle, the result is still individually unpredictable. Only when the results from both sides are later compared through ordinary communication do the correlations become clear. Their ordinary comparison still cannot travel faster than light. In this way, entanglement remains compatible with special relativity as a communication system. It is strange, but it is not a cosmic text message service with no signal delay. The universe thankfully has not given particles a secret group chat. Entanglement also does not prove mystical claims, cosmic consciousness, or the idea that everything is emotionally connected in a scientifically meaningful way. It is a precise physical concept with clear mathematical structure and experimental tests. The real version is already strange enough. It does not need decoration. Two quantum systems can share a state that produces correlations stronger than any allowed by simple local hidden variables. Yet those correlations cannot be controlled to transmit information faster than light. This makes entanglement one of the clearest examples of how quantum physics changes the meaning of reality without turning it into fantasy. Like tunneling, it takes an ordinary assumption and softens it. Tunneling says a barrier is not always the absolute ending classical physics would expect. Superposition says a quantum system may be described by a combination of possible states before measurement. The measurement problem asks why one definite outcome appears. Entanglement says separateness itself may not be as simple as it seems. In daily life, distance still works as expected. A book on one shelf is not mysteriously joined to a spoon in another room. Large objects are warm, complex, and constantly interacting with their environments, so their quantum relationships are usually hidden by decoherence. The classical world remains stable enough for ordinary experience, which is considerate of it. But beneath that stability, the quantum rules permit connections that are not built from tiny objects with fully independent properties. Entanglement reveals that the quantum world is not only uncertain or probabilistic, it is relational. What can be said about one system may depend on its connection to another. Physical facts are not always carried by isolated pieces of matter alone, but can belong to the shared structure between them. That is why entanglement feels so unsettling. It does not merely add another strange effect to the list. It quietly challenges the old image of reality as a collection of separate things, each carrying its own complete description through space. At the quantum level, nature seems more woven than that. Distance remains real. Light speed still matters. Signals still have limits. But separateness, the thing that once felt so obvious, becomes subtler, thinner, and far less simple than it first appeared. The word particle makes the quantum world sound as if it is built from tiny pieces of cosmic dust. An electron here, a photon there, a quark tucked inside a proton, all moving through empty space like beads sliding across an invisible table. This picture can be useful at first, Especially when thinking about experiments where detectors click, particles scatter, and energy arrives in separate packets. But modern physics suggests that this is not the deepest way to understand matter. Beneath the particle picture is quantum field theory. Quantum field theory is the framework that combines quantum mechanics with special relativity, and it is the foundation of modern particle physics. In this view, particles are not tiny permanent beads travelling through space as separate little objects. They are excitations of underlying fields. A field is something that has a value throughout space and time. The electromagnetic field is one familiar example, connected to electric and magnetic effects. In quantum field theory, every fundamental type of particle is associated with a field. The electron is connected to the electron field. The photon is connected to the electromagnetic field. Quarks are connected to quark fields. Gluons are connected to the gluon fields of the strong nuclear force. A particle, then, can be thought of as a kind of ripple or excitation in a field. This comparison is not perfect, because quantum fields are not ordinary fluids or waves in water, but it points in the right direction. A photon is not a tiny glowing pebble flying through nothingness. It is a quantum of the electromagnetic field. An electron is not a little charged marble that exists independently of everything else. It is an excitation of the electron field, with properties such as mass, electric charge, and spin arising from the structure of the theory. This is a strange shift, but also an elegant one. Instead of imagining the universe as a stage filled with tiny objects, quantum field theory presents reality as a collection of fields whose excitations appear as particles. The fields are more fundamental than the particle-like events observed in detectors. The detector sees a click, a track, or a transfer of energy. The theory beneath that event speaks in fields, probabilities, interactions, and allowed quantum states. One of the key steps toward this deeper picture came from Paul Dirac. In the late 1920s, Dirac developed a relativistic equation for the electron, bringing quantum mechanics into harmony with Einstein's special relativity. This was a major achievement because earlier quantum mechanics worked best at speeds far below the speed of light. Dirac's theory did something even more remarkable. It predicted the existence of antimatter. In particular, it pointed toward a particle with the same mass as the electron, but opposite electric charge, now known as the positron. When the positron was later discovered, it showed that quantum theory and relativity together could reveal entirely new pieces of reality before experiments had directly found them. Dirac's work helped open the road to quantum field theory, where particles could be created and destroyed as long as the deep conservation laws were respected. This mattered because relativity and quantum mechanics together do not allow a simple fixed number of particles in all situations. Energy can become particles. Particles can annihilate. Fields can exchange energy and momentum through interactions. Reality becomes less like a box of permanent beads and more like a restless set of fields capable of producing particle-like events. The most successful early example of quantum field theory is quantum electrodynamics, the theory of how light and matter interact through the electromagnetic force. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga played central roles in developing quantum electrodynamics into an extraordinarily precise theory. It describes interactions between electrons, positrons, and photons with astonishing accuracy. The theory is famous not only for being conceptually deep, but also for making predictions that match experiments to remarkable precision. Feynman introduced a powerful visual and mathematical language using what are now called Feynman diagrams. These diagrams are not literal pictures of tiny particles following little paths through space, though they are sometimes drawn that way. They are calculation tools that represent possible contributions to quantum interactions. Schwinger developed a highly rigorous operator-based approach, while Tomonaga independently worked out compatible methods in Japan. Together, their work helped show that quantum field theory could become not just philosophically interesting, but experimentally exact. From these foundations grew the Standard Model of particle physics. The Standard Model describes the known fundamental particles and 3 of the 4 known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It includes electrons and their relatives, neutrinos, quarks, photons, gluons, the weak force particles, and the Higgs field. The Higgs field is especially important because interactions with it help explain why many fundamental particles have mass. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed a major part of this framework. The Standard Model is not a theory of everything. It does not include gravity in the same quantum framework, and it does not explain dark matter, dark energy, or why the particle masses have exactly the values they do. But within its domain, it is one of the most successful scientific theories ever created. It turns the strange behavior of the quantum world into a detailed map of matter and forces. Quantum field theory also changes the way tunneling fits into the larger picture. Tunneling was first introduced through wave functions and barriers, where a particle can have a probability of appearing on the far side of a classically forbidden region. In field theory, that same general logic belongs to a broader world where fields can occupy different states, where interactions are probabilistic, and where processes can occur through paths that classical reasoning would never allow. Particle creation, annihilation, scattering, vacuum behavior, and tunneling are all part of a reality that is not built from little solid objects moving along obvious tracks. This does not make the particle picture useless. Physicists still speak of particles because experiments often detect localized events. A detector registers a photon. A particle accelerator records tracks and collisions. A medical scanner relies on interactions that can be understood in particle-like terms. But the deeper framework says those events are surface signs of field activity beneath. So the strange world of quantum physics becomes even stranger, but also more coherent. Matter is not simply made of tiny things. Light is not simply made of tiny sparks. Empty space is not merely a silent container. Beneath particles are fields, and beneath familiar objects are excitations, interactions, symmetries, and probabilities. Reality, at its deepest tested levels, seems less like a collection of hard little ingredients, and more like a quiet, structured music of fields. The particles are the notes that can be heard. The fields are the instrument underneath. Empty space sounds simple until physics looks at it closely. It seems as if removing all matter should leave behind nothing at all, a clean blankness where no particles, no atoms, no light, and no activity remain. In ordinary language, a vacuum is often imagined as absence. Take everything away, and the universe should be quiet. Perhaps even a little relieved to have some room. But quantum field theory changes that picture. In modern physics, the quantum vacuum is not a simple empty nothing. It is the lowest energy state of the fields that fill space. This distinction matters. A field does not vanish just because no particles are present. The electron field, the electromagnetic field, quark fields, gluon fields, and other quantum fields still exist as part of the structure of reality. A particle is an excitation of a field, rather like a note played on an instrument. The vacuum is the state where those fields have no real particles present, but the fields themselves have not disappeared. This means the vacuum is not empty in the everyday sense. It is not a box with every last thing removed. It is more like the quietest possible condition of the quantum fields. The fields are still there. Their rules are still there. Their possible excitations are still there. Space is not a passive stage waiting for matter to arrive. It has quantum structure even when it contains no ordinary particles. One reason this idea must be handled carefully is that popular explanations often say the vacuum is full of particles constantly popping in and out of existence. That phrase can be useful as a loose image, but it can easily become misleading. It can make the quantum vacuum sound like a tiny fireworks display of miniature objects appearing from nowhere, borrowing energy, then politely vanishing before the universe checks the receipt. That is not quite right. Vacuum fluctuations are better understood as features of quantum fields and their lowest energy state. They reflect the fact that fields cannot be perfectly still in the classical sense. Quantum uncertainty prevents field values and related quantities from being pinned down with unlimited precision. The vacuum has fluctuations, correlations, and measurable consequences, but these are not the same as ordinary particles flying around, waiting to be caught. Real particles can be detected directly as excitations carrying energy. Vacuum fluctuations are subtler. They are part of the mathematical and physical structure of the field state itself. One famous phenomenon connected to the quantum vacuum is the Casimir effect. In 1948, Hendrik Casimir predicted that two uncharged conducting plates placed extremely close together in a vacuum could experience a tiny attractive force. The broad idea is that the presence of the plates changes the allowed modes of the electromagnetic field between them and around them. Because the vacuum state of the field depends on those allowed modes, a small force can appear between the plates. The Casimir effect is often described as proof that empty space is full of energy, and in a careful sense it does show that the quantum vacuum has physical consequences. But it should not be oversold as if the plates are being pushed together by swarms of tiny invisible particles. The more careful explanation involves quantum fields, boundary conditions, and changes in the vacuum state caused by the conducting surfaces. It is still strange. It simply does not need to be made cartoonish in order to be interesting. Another important clue comes from the Lamb shift. In the late 1940s, Willis Lamb measured a tiny difference in the energy levels of hydrogen that earlier versions of quantum theory did not fully explain. This effect, now called the Lamb shift, became a major success for quantum electrodynamics, the quantum field theory of light and electrically charged matter. It showed that the interaction between an electron in an atom and the electromagnetic field affects the atom's energy levels in a measurable way. The Lamb shift matters because it reveals that quantum field effects are not confined to empty space as an abstract idea. They influence the structure of atoms. The energy levels of hydrogen, one of the simplest and most important atoms in the universe, are shifted slightly by the quantum behavior of the electromagnetic field. This is a small effect, but small does not mean unimportant. In precision physics, small effects are often where nature hides its most revealing signatures. Together, the Casimir effect and the Lamb shift point toward the same deeper lesson. The vacuum is not a classical void. It is not nothingness in the philosophical sense. It is a physical state of quantum fields, and because those fields are real parts of the universe, their lowest energy state can still have observable consequences. Empty space is empty of particles, perhaps, but it is not empty of structure. This idea also connects back to tunneling and the wider strange world of quantum physics. Tunneling showed that a barrier is not always an absolute ending. The wave function can extend into a forbidden region, leaving a small but real probability beyond it. Quantum fields widen that idea into a deeper landscape. Reality is not built from hard little objects moving through a blank emptiness. It is built from fields, field states, probabilities, interactions, and excitations. Even the quietest state of the fields is not the same as absolute absence. This does not mean the vacuum is a magical energy supply. It does not mean empty space can be treated like a hidden battery waiting to power a machine. The quantum vacuum has structure, but that structure is governed by strict physical laws. It cannot be casually harvested by wishful engineering or vague promises of unlimited energy. The real version is more restrained and far more beautiful. The vacuum is the universe at its quietest, not the universe removed entirely. It is the lowest note the fields can play, not the absence of the instrument. And from that quietest state come subtle effects that can be measured, calculated, and compared with experiment. So even emptiness belongs to the strange world of quantum physics. The space between things is not merely a gap, it is part of the physical story. It carries the rules of fields, the traces of uncertainty, and the possibility of interactions not yet excited into particles. At the deepest tested levels, nothing is not quite nothing. Even the silence has structure. Quantum physics can sound remote from life, as if it belongs only to particle accelerators, deep space, superconducting circuits, and laboratories full of equipment that looks expensive enough to make a university accountant breathe into a paper bag. But quantum mechanics is not separate from the living world. It is beneath it. Every cell, every protein, every strand of genetic material, every breath of oxygen carried through blood depends on chemistry, and chemistry depends on quantum physics. The reason is simple, though the details are wonderfully deep. Chemistry is mainly the story of electrons. Electrons determine how atoms bond, how molecules form, how substances react, how materials conduct electricity, how pigments absorb light, how enzymes help reactions happen, and how the structures inside living cells hold together. But electrons are quantum objects. They are not tiny planets circling atomic nuclei in neat little loops. They occupy orbitals, which are quantum states described by wavefunctions and probability distributions. These orbitals help determine where electrons are likely to be found and how they can participate in bonding. Atomic bonding is quantum from the start. When atoms approach one another, their electron wavefunctions can overlap. The allowed arrangements of electrons, along with the energy levels available to them, help decide whether a bond forms and what kind of bond it is. Covalent bonds, ionic bonds, metallic bonds, and the weaker interactions that shape large biological molecules all rest on quantum rules. A molecule is not just atoms clipped together like beads on a string. It is a quantum structure, held by the behavior of electrons shaped by energy, symmetry, electric charge, and the Pauli exclusion principle, which prevents certain particles from occupying the same quantum state. Linus Pauling played a major role in bringing quantum mechanics into chemistry. His work helped explain chemical bonding, molecular structure, and the shapes of molecules using quantum ideas. Pauling showed that chemistry could be understood not merely as a collection of recipes and reactions, but as a deep physical science rooted in the behavior of electrons. The structure of molecules, the strength of bonds, and the shapes that atoms prefer are not arbitrary. They emerge from quantum mechanics operating at the scale where chemistry happens. This matters enormously for life. Proteins fold into specific shapes because their atoms interact according to quantum-governed chemistry. DNA holds genetic information because its molecular structure is stable enough to preserve information, yet reactive enough to be copied and repaired. Water has its remarkable properties because of the structure of its molecules and the interactions between them. The oxygen used in respiration, the carbon dioxide released afterward, the sugars broken down for energy, and the fats stored for later are all part of a chemical world whose foundations are quantum mechanical. One place where tunneling can reappear is in chemical reactions involving hydrogen. A proton, the nucleus of a hydrogen atom, is very light compared with most atomic nuclei. Because it is light, its quantum nature can sometimes become important in reactions where hydrogen moves from one place to another. Proton tunneling can influence certain hydrogen transfer processes, allowing a proton to pass through an energy barrier rather than simply crossing over it in the classical way. This can affect reaction rates and pathways in some chemical systems. In biology, proton movement is especially important because many enzymes, membranes, and energy processes involve hydrogen ions and changes in charge. Enzymes are biological catalysts, meaning they help reactions happen more easily by lowering the energy barriers involved. In some enzyme reactions, proton tunneling may contribute to how quickly or efficiently certain transfers happen. This does not mean enzymes are magical quantum machines, solving mysteries with tiny secret trapdoors. It means that, at the molecular scale, some biological chemistry can involve quantum effects in ordinary physically lawful ways. That distinction is important. Quantum effects are essential to life because chemistry itself is quantum. But it is not accurate to say that life is mysterious simply because it is quantum, or that every biological process relies on dramatic quantum weirdness. Much of biology can be described very successfully through chemistry, thermodynamics, molecular biology, and classical approximations that work well at larger scales. The quantum foundation is real, but not every biological event is a delicate entanglement experiment hiding in a leaf or a liver cell. Photosynthesis is one of the most interesting places where quantum ideas have been discussed carefully. In photosynthesis, plants, algae, and some bacteria capture light and use its energy to help build chemical fuel. When a pigment molecule absorbs a photon, the energy can create an excited state called an exciton. This exciton is not a particle in the same sense as an electron flying freely through space. It is a mobile packet of excitation energy that can move through a network of molecules toward a reaction center, where the energy begins to be converted into chemical form. Some research has suggested that quantum coherence may play a limited role in how excitation energy moves through certain photosynthetic complexes under specific conditions. Quantum coherence means that wave-like relationships between possible pathways remain organized long enough to influence behavior. In simple terms, the energy transfer may sometimes explore molecular routes in a way that cannot be described as a tiny classical object hopping blindly from one place to another. But this subject must be handled cautiously. Living systems are warm, wet, noisy environments, and delicate quantum coherence is usually difficult to preserve there. The evidence points to subtle, context-dependent quantum effects, not a mystical green superpower operating in every leaf like a botanical quantum computer. Still, even cautious examples are fascinating. They show that quantum physics is not locked away from life. It appears wherever the scale becomes small enough and the conditions allow quantum behavior to matter. Electron orbitals shape molecules. Molecular energy levels determine which wavelengths of light are absorbed. Proton tunneling can influence some reactions. Excitons help describe light energy moving through photosynthetic systems. The living world is built from chemistry, and chemistry is built from quantum mechanics. This gives the strange world of quantum physics a softer and more familiar face. It is not only a story of particles crossing barriers, photons passing through slits, entangled systems challenging separateness, or empty space holding the quiet structure of fields. It is also part of the reason a flower has colour, a leaf can harvest sunlight, an enzyme can guide a reaction, and a cell can maintain the intricate chemistry needed to stay alive. Quantum physics does not make life less natural. It makes nature deeper. The same rules that seem strange in laboratories are also quietly present in the ordinary chemistry of breathing, growing, healing, tasting, thinking, and sleeping. Life is not an exception to physics. It is one of physics' most elaborate arrangements. Beneath biology, there is chemistry. Beneath chemistry, there are electrons, orbitals, bonds, energy levels, tunneling, and wavefunctions. And beneath the familiar warmth of living things, the quantum world continues its quiet work, not as a spectacle, but as the delicate structure that makes life possible. For much of its history, quantum physics seemed like a theory about what nature was doing whether humans understood it or not. It explained atoms, light, radioactivity, tunneling, chemical bonds, and the strange behavior of matter at small scales. But over time, something remarkable happened. The strangest features of quantum theory stopped being only puzzles to interpret. They became resources to use. This is the idea behind quantum information. Quantum information is the field that treats superposition, entanglement, and measurement not merely as mysteries, but as practical tools for processing, transmitting, and measuring information. In ordinary computing, information is usually stored in bits. A bit can take one of two possible values, like a tiny switch being off or on. This simple idea underlies the vast digital world of phones, computers, servers, streaming videos, bank transfers, weather models, and all the other invisible electronic fuss that keeps modern life both convenient and mildly exhausting. Quantum information uses qubits. A qubit is a quantum system used to store and process information. It might be represented by the state of an ion, the spin of an electron, the polarization of a photon, or a carefully designed superconducting circuit. But a qubit is not just an ordinary bit that casually holds both values at once in the everyday sense. That phrase is common, but it can be misleading. A qubit is described by a quantum state, and that state can be a superposition of the possible measurement outcomes. When measured in a particular way, it gives a definite result, but before measurement, its behavior is governed by the rules of quantum probability. This subtle difference is where the power and difficulty begin. A single qubit does not simply store more ordinary information than a bit in a straightforward way. Measuring it still gives one result. The advantage comes from how many qubits can be arranged, transformed, entangled, and measured so that quantum interference strengthens useful outcomes and suppresses unhelpful ones. Quantum computing is not magic parallel computing, where every answer is checked at once like an over-enthusiastic librarian with infinite arms. It is a carefully controlled use of quantum states to solve particular kinds of problems in new ways. David Deutsch was one of the important figures in developing the theoretical foundations of quantum computing. He showed that computation itself could be considered through the rules of quantum mechanics, helping establish the idea of a universal quantum computer. Later, Peter Shor developed a famous quantum algorithm showing that a sufficiently powerful quantum computer could factor large numbers far more efficiently than known classical methods. This mattered because much of modern encryption depends on the practical difficulty of factoring large numbers. Lovegrover developed another famous algorithm, showing that quantum computers could speed up certain search problems. These ideas did not make quantum computers instantly practical, but they proved that quantum information was not just a philosophical game. Today, quantum computing is one of the most active areas of research in physics, engineering, computer science, and material science. Organizations such as IBM Quantum, Google Quantum AI, the University of Science and Technology of China, and many university and national laboratory groups are working on different approaches. Some use superconducting circuits, where Josephson junctions play a key role. Some use trapped ions, held and controlled with electromagnetic fields and lasers. Others explore photons, neutral atoms, defects in crystals, and other physical systems. Each approach has strengths and difficulties, and all must confront the same basic enemy: noise, Quantum states are delicate. They can be disturbed by heat, stray fields, vibrations, unwanted interactions, and imperfect control. Decoherence, which makes the everyday world look classical, is a serious challenge for quantum machines. A quantum computer must keep enough coherence for its qubits to behave quantum mechanically, while also allowing those qubits to be controlled and eventually measured. This is rather like trying to keep a soap bubble intact while using it as a calculator. Beautiful, possible in principle, but not exactly relaxing for the engineers. Quantum sensing is another major area where quantum behavior becomes useful. Quantum sensors use fragile quantum states to detect tiny changes in the world. Atomic clocks, which rely on precise transitions between quantum energy levels, are among the most accurate measuring devices ever built. They support global navigation systems, tests of fundamental physics, and measurements of time so precise that even gravity's effect on clock rates can become detectable across small height differences. Other quantum sensors can measure magnetic fields, acceleration, rotation, electric fields, and gravitational effects with extraordinary sensitivity. National metrology institutes, which maintain measurement standards, are deeply involved in this work, because precision measurement is one of the quiet foundations of modern science and technology. Quantum communication uses quantum systems to transmit information in ways that can reveal interference or eavesdropping. One important area is quantum key distribution, where the laws of quantum measurement can help two parties detect whether a communication channel has been disturbed. Entanglement is also studied for future quantum networks, where quantum states might be shared between distant nodes. This does not allow faster-than-light messaging, and it does not make communication magically unbreakable in every practical sense. Real systems still have losses, hardware flaws, and engineering challenges, but it shows how the odd rules of measurement and entanglement can be turned into new ways of thinking about security and connection. All of this connects back to tunneling and the earlier strangeness of quantum physics. In superconducting quantum circuits, Josephson junctions depend on quantum tunneling between superconductors. In semiconductors and memory devices, tunneling helps shape how charge moves through barriers. In quantum computing, superposition and entanglement become parts of calculation. In quantum sensing, delicate energy levels and phase relationships become tools for measurement. In quantum communication, the act of measurement itself becomes part of the security. The strange world of quantum physics, then, is no longer only something scientists observe from the outside. It is being engineered. The same rules that once made particles seem baffling are becoming components in machines. Probability, once unsettling, becomes a design feature. Superposition, once a conceptual headache, becomes a resource. Entanglement, once an argument about separateness, becomes something that can be distributed, tested, and used. These machines are still developing, and many promises should be treated carefully. Quantum computers will not replace all ordinary computers, and they are not magic devices that instantly solve every problem. Their likely power lies in specific tasks, such as simulating quantum systems, exploring some optimization problems, improving certain calculations, and breaking or reshaping parts of cryptography if large, fault-tolerant machines are achieved. But even in their unfinished state, quantum technologies reveal something profound. The deepest strangeness of matter is not merely hidden beneath reality. It can be shaped into instruments, circuits, clocks, sensors, and channels of communication. What once sounded like nature refusing to behave sensibly is becoming a new layer of engineering. The quantum world has not become less strange, it has become useful. Quantum physics feels strange because it asks the human mind to think outside the conditions that shaped human intuition. Everyday experience is built from large, warm, slow objects surrounded by air, light, heat, sound, and constant interaction. A cup stays on a table. A door is either open or closed. A person is in one room and not another. A wall remains professionally committed to being a wall. These habits are so reliable that they begin to feel like the deepest rules of reality. But they are not the deepest rules. They are the large-scale result of something quieter underneath. At small scales, matter and light are described through wavefunctions, probabilities, quantum states, and measurements. A particle is not simply a tiny marble following one hidden path. A barrier is not always an absolute ending. A quantum system may be described as a superposition of possible states. Two systems may be entangled so that they must be described together, even across distance. Empty space is not merely a blank stage, but the lowest energy state of quantum fields. The familiar world is still real, but it's built from foundations that do not behave in familiar ways. Quantum tunneling reveals this with unusual clarity. Classical physics says that if a particle does not have enough energy to cross a barrier, it should not appear on the far side. Quantum mechanics says the wave function can extend into the barrier, fade within it, and sometimes leave a small but real probability beyond it. That probability may be tiny, but it is not always zero. In radioactive decay, tunneling helps alpha particles escape from atomic nuclei. In the Sun, tunneling helps protons get close enough for nuclear fusion to occur. In modern technology, it appears in tunnel diodes, flash memory, Josephson junctions, and scanning tunneling microscopes. The impossible shortcut is not a fantasy. It is a working feature of nature. The wave function deepens that lesson. It does not describe a particle as a little object with every property neatly settled in advance. It describes the possible states of a system and how those possibilities evolve. Through Max Born's interpretation, the wave function became tied to probabilities of measurement outcomes. That does not make quantum physics vague. It makes probability precise. Nature is not shrugging. It is giving answers through a different grammar. Heisenberg's uncertainty principle shows that this grammar has limits built into it. Position and momentum cannot both be known with unlimited precision at the same time. This is not simply because instruments are clumsy. It arises from the wave-like structure of quantum systems. A sharply confined particle must have a wider spread of possible momenta, while a particle with a more definite momentum is less sharply located. This helps explain why atoms do not behave like tiny solar systems, and why electrons form orbitals rather than neat little planetary tracks. The uncertainty is not a failure of knowledge, it is part of what makes matter stable. Superposition adds another layer. A quantum system can be described as a combination of possible states before measurement. Electron spin, photon polarization, and atomic energy states can all involve superpositions. These are not ordinary objects being casually indecisive in everyday terms. They are quantum systems whose possible outcomes can interfere, combine, and produce measurable patterns. Schrödinger's cat became famous because it exposed the difficulty of applying this idea too simply to large objects. The cat was not meant as a cute mascot for quantum weirdness. It was a warning that the link between quantum possibilities and definite outcomes remains conceptually difficult. That difficulty leads to the measurement problem. Quantum theory often gives probabilities before measurement, but definite outcomes afterward. A detector clicks in one place, a photon is found with one polarization, an electron leaves one mark. Niels Bohr and the Copenhagen interpretation placed measurement at the center of what can be said about a quantum system, while other interpretations offer different ways to understand what the wave function means. The question remains open not because quantum mechanics fails, but because it succeeds so precisely while leaving behind a deeper mystery about what counts as a physical fact. Entanglement makes separateness less simple. The Einstein-Podolsky-Rosen argument challenged quantum theory by asking whether distant systems could really be described in such a deeply linked way. John Bell later showed that the issue could be tested. Bell tests, including the work of Alain Aspect and later loophole-reduced experiments, showed that nature does not fit simple local hidden variable explanations. Entanglement does not allow faster-than-light messaging, and it does not break relativity as a communication system. But it does show that quantum systems can share a state in a way that ordinary separateness cannot fully capture. Quantum field theory widens the picture again. Particles are not tiny permanent beads moving through empty space. They are excitations of underlying fields. Quantum electrodynamics, developed through the work of Richard Feynman, Julian Schwinger, and Zenitiro Tomonaga, describes interactions between light and charged matter with extraordinary precision. The Standard Model extends this field-based view across electrons, photons, quarks, gluons, weak force particles, and the Higgs field. Particle accelerators such as the Large Hadron Collider do not merely smash little pellets together. They probe the field structure beneath a matter, and this strange framework works. It supports atomic clocks, lasers, semiconductors, magnetic resonance imaging, particle physics, quantum sensors, and emerging quantum computers. Bell tests confirm the non-classical structure of entanglement. Quantum electrodynamics matches experiment with astonishing accuracy. Semiconductors and lasers quietly power the modern world. Atomic clocks measure time so precisely that relativity and quantum mechanics meet in technologies used for navigation and scientific measurement. Still, the story is unfinished. The measurement problem remains debated. The interpretation of the wave function is not settled. The relationship between quantum physics and gravity remains one of the largest open questions in science. General relativity describes gravity as the curvature of space-time, while quantum theory describes matter and forces through probabilities, states, and fields. Bringing those pictures together has not yet been achieved in a complete experimentally confirmed theory. So quantum physics feels strange because it is not built for human intuition. Human senses evolved to handle animals, tools, weather, landscapes, food, danger, and other large-scale concerns. They did not evolve to picture wave functions, tunneling probabilities, entangled states, or quantum fields. The surprise is not that the quantum world feels strange. The surprise is that the human mind can understand as much of it as it does. Quantum physics does not make reality meaningless. It does not turn the universe into chaos, imagination, or magic. It reveals something more disciplined and more unsettling. Reality is lawful, but not always classical. It is stable, but built from probability. It is familiar at the surface, but deeply structured underneath. The strange world of quantum physics is not separate from the ordinary world. It is the quiet machinery beneath it, shaping atoms, light, chemistry, stars, technology, and empty space itself. The universe is not making things up as it goes. It is following rules that are far more subtle than common sense expected. The strange world of quantum physics is not somewhere else. It is not sealed away in distant laboratories, hidden only inside particle accelerators, or waiting at the edge of imagination. It is beneath the familiar world, quietly shaping the matter, light, chemistry, and technology that make ordinary life possible. A barrier that seems uncrossable can become a place where probability leaves a faint opening. A wave function can describe not one fixed path, but a structured landscape of possible outcomes. Radioactive atoms can decay through tunneling. The sun can shine because protons sometimes pass close enough through their electric barrier for fusion to begin. Modern electronics can store information, guide currents, and sense the world through quantum effects that once seemed almost impossible. Then the strangeness widens. Heisenberg's uncertainty principle shows that nature does not allow every property to be sharpened without limit. Superposition reveals that quantum systems can carry combinations of possible states before measurement. The measurement problem asks why one definite result appears from many possible outcomes. Entanglement shows that separateness is not always as simple as distance makes it seem. Quantum fields suggest that particles are not tiny permanent beads, but excitations of deeper fields. Even the vacuum is not plain nothingness, but the lowest energy state of a structured physical world. And still, this is not mysticism. It is not vagueness, fantasy, or the universe becoming careless with its own rules. Quantum physics is strange because it is precise in a way ordinary intuition was never built to expect. It supports semiconductors, lasers, atomic clocks, material science, particle physics, magnetic resonance imaging, and emerging quantum technologies. It is one of the most successful scientific frameworks ever created, even while some of its deepest meanings remain open. The familiar world remains solid enough to trust. Walls stay walls, tables hold cups, sunlight warms the room. But underneath that calm surface, reality is quieter, stranger, and more delicate than it first appears. The ordinary world is not less real because of quantum physics. It is more deeply real than it ever seemed.